Welcome to this video on the natural colors of infinite words. In this video, we will see how we can generalize the concept of the color of a word in a parity automaton to the omega regular language level, and how that gives rise to a new canonical form representation of arbitrary omega regular languages. Let us start with the importance of canonical forms in automata theory. In automata theory, a classical question is which automata types admit a canonical form that can be computed in polynomial time. A canonical automaton for a given language is a unique representative of all automata accepting the given language. Canonical forms often give insight into the structure of the language represented. For instance, for deterministic automata over finite words, the classical Myhill-Néraud theorem tells us that every such automaton can be translated to one in which the suffix languages of the states are unique. Hence, a canonical automaton is a representation of the suffix languages of a given language. This slide contains an example. The automata on the left-hand side both represent the same language. For each of them, translating the automaton to its canonical form yields the automaton on the right-hand side. It only has two states, as there are only two different suffix languages in the given language. It is hard to think of a canonicity definition that does not come with minimality of the automata, as it does for deterministic automata over finite words. And hence, canonical automata also often serve as a minimally sized representation of the language of interest. For automata over finite words, it is well known how difficult it is to compute canonical automata. A canonical minimal version of a deterministic automaton over finite words can be computed in polynomial time, using the already mentioned Myhill-Néraud theorem. For non-deterministic automata, which can be smaller than deterministic automata, computing a canonical version has a higher complexity. Since checking if such an automaton accepts all possible words is piece-space hard, and by computing a canonical automaton and comparing it against the automaton for the universal language we can also test for universality, it follows that computing a canonical form is at least piece-space hard, regardless of the concrete canonicity definition used. Apart from automata over finite words, there are, however, also automata over infinite words. These are often used to reason about the properties of reactive systems, which are computational systems that operate in steps, do not terminate, and in each step of their execution have a state. Let us consider an example, namely the one depicted on the slide. We consider a simple coffee machine controller. It has one input proposition and two output propositions, and it executes in clock cycles. The input proposition request should, at every point in time, denote whether the coffee request button of the coffee machine having this controller is pressed. And then this controller is supposed to trigger the grinding and brewing units of the coffee machine. If we observe the execution of such a controller, what we're getting is an infinite so-called run of the system. In every step, each of the atomic propositions has a value of either true or false. This run consists of letters, and since here we have 3 atomic propositions, there are 8 different possible letters. This run is, by the way, infinite, because we are assuming that the coffee machine controller never terminates, and it continues executing until the coffee machine is eventually switched off, which however is not modeled. So the run is, at least in principle, infinite. Such a coffee machine controller can also have a specification. And part of the specification could be that whenever the user requests a coffee by pressing the respective button, the grinding unit should eventually later start to work. And the specification could then be represented in the form of an automaton over infinite words. Such an automaton can then be used as a more technical representation of the specification, which allows us to model check a given coffee machine controller against the specification, or to alternatively synthesize a coffee machine controller implementation from the specification. An automaton over infinite words accepts or rejects words. And in order to understand what an automaton is doing, we have to understand which words it accepts and which words it rejects. Here, for instance, we have a so-called deterministic Büchi automaton. It accepts all words that induce runs of the automaton on which accepting states are visited infinitely often. These are drawn doubly circled as done here. A run of this example automaton stays in the left-hand state until a request is seen that is not immediately answered by the coffee machine controller with a grinding action. So while not R is true or G is true, a run stays in state Q0, taking the self loop here. Only when a request is seen that is not immediately answered by grinding, then the run of the automaton switches to state Q1. And in Q1, the run stays until grinding is seen, and then the run goes back to state Q0. With this concrete automaton here, exactly the words for which eventually a request happens that is not later answered by grinding are rejected. And all other words lead to runs that visit Q0 infinitely often, and hence they are accepted. Now that we know what automata over infinite words are good for, let us now have a look at how and if we can compute canonical forms of such automata. Again, we have to distinguish between different types of such automata. Let us start with non-deterministic Büchi automata. These are the non-deterministic generalization of the Büchi automata that we have seen on the previous slide. They are often used in model checking. Unfortunately, the p-space hardness argument for non-deterministic automata over finite words also applies here. For very simple deterministic automaton types, we can, however, compute a canonical form of such an automaton in polynomial time. For instance, the polynomial time procedure for computing canonical deterministic automata over finite words can also be used in the infinite word case for deterministic safety automata. In such an automaton, all states are accepting except for the one that rejects all words. Such automata can represent safety languages, which intuitively state that something bad should never happen. Here, on the right-hand side of the slide, we have an example for such a safety automaton. It represents that grinding should always be preceded by a request right before the grinding occurs. And this request has to be given after the last time that grinding occurred in the past. Rüdiger showed that this idea can be extended to deterministic weak automata. In weak automata, states in the same strongly connected component need to be all accepting or all non-accepting. Weak automata can express more properties than safety automata, but are still unable to express all so-called omega regular properties. Especially the so-called liveness properties cannot be expressed by weak deterministic automata. The simplest automaton model able to express at least some liveness properties are deterministic Büchi automata, which we have already seen. Schewe showed that, unfortunately, they are NP hard to minimize, which rules out canonicity definitions that also come with minimality, which is what we are normally interested in. With deterministic Büchi automata being NP hard to minimize, this also applies to deterministic co-Büchi automata, which accept all words for which the corresponding automaton runs visit marked states only finitely often. When interpreting the example automaton on the slide as such, it accepts words for which grinding occurs only finitely often. It turns out, however, that the NP hardness result by Schewe crucially requires the states of the automata to be accepting or non-accepting, rather than the transitions. For automata with transition-based acceptance, Schewe did not provide any results. Whether deterministic Büchi or co-Büchi automata with transition-based acceptance are NP hard to minimize is currently unknown. Interestingly, when further generalizing from deterministic co-Büchi automata to so-called good-for-games co-Büchi automata with transition-based acceptance, there is, since recently, a polynomial time procedure for making an automaton canonical and also minimal in the number of states. Such good-for-games automata extend determinism of the transitions, but only very slightly. They are a special case of non-deterministic co-Büchi automata. And, by the way, all of these co-Büchi automaton types are all equally expressive. In a good-for-games automaton, the non-determinism can be resolved by looking at the history of the word alone. And a word is accepted by the resulting run if and only if there exists an arbitrary run of the automaton accepting the word. For instance, consider the good-for-games co-Büchi automaton here on the slide. The rejecting transitions are dashed, and this automaton accepts those words over the letters A, B, and C for which either at some point A's do not occur anymore, or at some point C only occurs at even or odd positions in the word, but not at both even and odd positions. The automaton consists of two strongly connected components when considering only the accepting transitions. The two strongly connected components, short SCCs, capture the two types of words that should be accepted. A run satisfying one of them can get stuck in the respective strongly connected component. Non-deterministic rejecting transitions allow the run to switch between the strongly connected components. This automaton is good for games, because whenever along a run of the automaton a next letter is read that leads to non-deterministic choice, then non-deterministic transitions between the strongly connected components can be taken. And for resolving the choice when starting from Q2, one can take the leftmost transition if the last C was seen an even number of letters ago, and otherwise a transition to Q1 can be taken. When considering the possible runs of the automaton when following this strategy, we can see that the automaton accepts a word with a strategy for resolving non-determinism if and only if there exists some accepting run for the automaton. Hence, this automaton is good for games. This automaton is, by the way, also an example for the fact that a good for games automaton can be smaller than the smallest deterministic automaton in the co-Büchi case with transition-based acceptance. The smallest deterministic co-Büchi automaton for this language needs 4 states, but here we only have 3 states. Motivated by these positive results, there's now the question if the polynomial time results for automaton, minimization, and computing canonical automata can somehow be extended to full omega regular languages. For these, neither co-Büchi nor Büchi acceptance is enough for deterministic or good for games automata, and we need to generalize to parity acceptance. Unfortunately, at least for state-based acceptance, we obtain NP hardness for minimizing good for games parity automata. While for transition-based acceptance, the complexity is still open, perhaps there's a way to circumvent the problem and obtain a canonical form for arbitrary omega regular languages based only on the positive results that we have. So let us see how this could be done. Let us start here with a transition-based deterministic parity automaton, such as the one here on the slide. To keep this and later examples simple, let us henceforth consider alphabet letters rather than expressions over propositions. Such a parity automaton has a color assigned to each transition. For instance, the self loop over character A on the initial state Q0 has color number 1. A run of this automaton is built from a word in the usual way, and we obtain an infinite sequence of colors visited along the run. The color of a word or the run induced by the word is now the least color occurring infinitely often along the run. And the word is accepted by the automaton if and only if the color of the corresponding run is even. For instance, the word A repeated for eternity is rejected by the automaton because the color of the respective run is 1. And that is because 1 is actually the only color visited along the run, starting in state Q0 and taking the self-loop over A on Q0 all of the time. Such a parity automaton can be decomposed into multiple co-Büchi languages. In this example, there are 3 such languages. L1 accepts the words with color at least 1, L2 accepts the words with color at least 2, and L3 accepts the words with color at least 3. We could also define L0, but every word has a color of at least 0 in the parity automaton, because that is the least color. So L0 is the universal language. Similarly, L4 and above are all empty languages, so we don't need to explicitly state them here. These languages, L1 to L3, can all be represented by co-Büchi automata. For instance, if the color of a word is at least 1, then transitions with color 0 must only be visited finitely often along a run of the parity automaton. So we can obtain a deterministic co-Büchi automaton for L1 by taking the parity automaton and making exactly those transitions accepting that have a color of at least 1. And implementing this idea yields this automaton here. It has 2 rejecting transitions because in the parity automaton there are 2 transitions with color 0. Similarly, we can get a co-Büchi automaton for L2 by copying the transition structure of the parity automaton and making those transitions accepting, for which in the parity automaton we have a color of at least 2. And the automaton for L3 can be built in the same way. The co-Büchi automata together still represent the original language, if we define that they together accept a word if and only if the greatest index I such that Li accepts the word is even. So we decomposed an omega regular language into multiple co-Büchi languages. By the construction of these automata, we have that the words accepted by L1 are a superset of the words accepted by L2. And the words accepted by L2 are a superset of the words accepted by L3. So we have a falling chain of languages. Since each of these automata for L1 to L3 are co-Büchi automata, each of them can now be made canonical using the procedure by Abu Radi and Kupferman. In this case, the automaton for L1 becomes a lot smaller, but the others do not actually change in size, and only some transitions become rejecting when making the automata canonical. And since now the automata for the languages L1, L2, and L3 are all canonical, we could consider the chain of automata for L1, L2, and L3 to be a canonical representation of the language of the parity automaton. Well, not quite, as there's still a problem. The individual automata are canonical for the languages L1 to L3, but the decomposition of the original language into these co-Büchi languages is not unique. To see this, consider the word A to the power of omega again. So A repeated for eternity. This one is in L1, but not in L2. It is in L1 because in this automaton only accepting transitions are taken for this word. But in this automaton, this rejecting transition from Q0 back to Q0 is taken all of the time. But it turns out that the parity automaton at the top of the slide can be simplified by making Q2 the initial state and removing Q0. That is possible because Q0 and Q2 have the same language, and then Q0 is not reachable anymore. The automaton resulting from changing the initial state hence still accepts the same language. But then the color of a to the power of omega becomes 3, and hence it is now accepted by L2. And as a consequence, this decomposition idea for obtaining a canonical representation for an omega regular language doesn't yet work, as the chain of co-Büchi automata is not actually canonical. Now, how can we make it work? Well, if we had a way to define a color for each word based on the language to be represented alone, and not on the automaton representing the language that we start with, then all of the languages Li would be canonical, and hence this chain of co-Büchi languages would be a canonical representation of the overall omega regular language that we want to represent. And we call this color of a word defined by the language to be represented alone the natural color of a word. How to define this natural color of a word is the main question addressed in this work. And its answer gives rise to a canonical representation of an omega regular language in the form of a chain of co-Büchi automata. And this definition of the natural color of a word is exactly what we provide in this work. It is based on the language to be represented alone, and the color of a word does not depend on how such a language is represented. While our definition is not the only one conceivable, it has a couple of properties that one would like to have for such a definition. First of all, despite the definition of the natural color of a word not using the representation of a language, it is still easy to compute the natural color of a word from an automaton representation of the language. More precisely, this holds for a deterministic parity automaton as representation, as we will see. Secondly, the co-Büchi automata for the languages Li, to which the language to be represented is decomposed, are also small. They never need to have more states than any deterministic parity automaton representing the language. As the second contribution, we show that the definition of the natural color of a word gives rise to a polynomial time algorithm for computing the chain of co-Büchi automata representation of the language. We will see later that the algorithm is actually quite simple, which underlines the statement that our definition of the natural color of a word is, well, quite natural. For the remainder of this talk, these two contributions will be presented. We start with the definition of the natural color of a word, and then look at an algorithm for decomposing a deterministic parity automaton into a chain of co-Büchi languages. So how can the natural color of a word be defined? To see this, let's have a look at what colors are needed for when building a deterministic parity automaton for a language, and let us step by step make some observations guiding us towards an automaton agnostic version of the color of a word. So how are colors used in parity automata? Why do some languages need 2 colors and others 3? This is answered in a paper by Nivinsky and Walukiewicz, where they described a procedure to minimize the number of colors that a given parity automaton for a language needs to have. In particular, they searched for so-called flowers in an automaton, and these flowers prove that a certain number of colors is needed. And they then reduce the number of colors in a given automaton until a flower is present that proves that this number of colors is really needed. A flower consists of a center state, and a flower path from the center state back to itself. Along different flower paths, the least color visited is different. In this example, and for QC as the center state, we have flower paths for the colors 5, 4, 3, 2, and 1. If we have a certain number of flower paths for which the least colors alternate between being even or odd, then this proves that this number of colors is needed to represent the automaton's language, as Nivinsky and Walukiewicz showed. But why is that? It is because the flower loops give rise to a hierarchy of words that alternate between being accepted and being non-accepted. Let us have a look at this idea in detail. At the top of the slide, you can find the example automaton from the previous slide. Let us now consider a word built by considering only the flower loop with the highest color. This could, for instance, be the word consisting of an infinite repetition of CA. In this case, only the transitions between QC and Q3 are taken, and these both have colors of 5. Thus, the lowest color visited infinitely often along the run is 5, and since it is odd, the word is rejected by the automaton. Now let us assume that we take this word with color 5 and inject the flower loop with color 4 infinitely often at places in which the run is in the center state. We can do so by injecting the letters of the flower loop with color 4 at the positions in the word in which the run is at state QC. This yields this new word here on the slide, whose dominating color is now 4. It consists of letters that let the run alternate between the two flower loops considered so far. Similarly, we can inject a flower loop with color 3 into the word and the run, a flower loop with color 2, and finally a flower loop with color 1. This hierarchy of words now constitutes a reason for why in this example 5 colors are needed. The finite state automaton needs to distinguish between whether a finite or an infinite number of flower loops are inserted into the words in this hierarchy, and the only way for a finite state parity automaton to do this is by having 5 colors. Additionally, it is important if the lowest of these 5 colors is even or odd, and in this example it has to be odd. To define the natural color of a word, we can build on the idea to understand the role of colors as keeping track of finite words that can be inserted into the word and that, if inserted infinitely often, need to change the color of a word. The flower loops by Niewinski and Walukiewicz have the property that they lead from a state back to the same state. And for an automaton-agnostic definition of the natural color of a word, we can't build on the notion of state and have to generalize the idea so that it doesn't refer to states anymore. So how can we solve that? Well, we can ask ourselves what the role of a state is on the language level. Every state actually defines a language, namely the set of words that it accepts when a run starts in the state. When a state is not initial, but can only be reached via some prefix words, like it is the case here with Q1 and Q2, the state still represents a language, which we can call a suffix language. Here in this example, there are 3 states in the parity automaton, and there are only 2 different suffix languages. Now we can lift the idea of flower loops to the language level by working with suffix languages rather than center states. Let us see how this can be done, and to keep things simple, we want to start with the case of the most significant color. The nice thing about the most significant color is that a word having this color is robust against flower loop insertions. Let us, for example, consider the word consisting only of Cs in this example automaton. Whether the word is accepted or not does not change when inserting additional flower loops, because the induced run already visits the most significant color in the automaton infinitely often. To lift the idea of flower loops to the language level, we now want to reformulate the concept of a flower loop to make use of the observations that we made on the previous 2 slides. We can do that as written here on the slide. The suffix languages will take the role of the center state, and at these we will add words that lead back to the same suffix language. We say that these are suffix language invariant. With this idea in mind, we can now define a first version of when the natural color of a word is the most significant color. And that is the one here. We say that a word W has the most significant color if no injection of suffix language invariant finite words at infinitely many places in the word changes whether W is in the language. This definition indeed captures the idea of flower loops at the language level. If no matter what is injected into the word does not change whether the word is accepted, provided that the injected words are all suffix language invariant wherever they are injected, then this characterizes the most significant color well. Unfortunately, this definition is too strong and not yet what we are searching for. To see this, let us consider an example. The automaton shown here accepts those words over the alphabet consisting of the letters A and B for which infinitely often two A's occur successively. This is because the only way for a run to visit a transition with color 0 is when two A's have been seen in a row. Words for which this does not happen infinitely often obtain a color of 1 and are rejected. There are only two colors here, one of which is accepting and the lowest color. The other color is the higher color and it is rejecting. Hence, it would make sense if exactly the words accepted by the automaton are the ones with the most significant color. In this example, both states have the same suffix language. And an accepted word can be made non-accepted by injecting a B between every two consecutive A's. But in this automaton, 0 is the most significant color. And then there can be no word that has a natural color of 0 when using the definition from before, as we can make every word non-accepted by injecting suffix language invariant finite words. And no word having the most significant color makes no sense. The example, however, provides us some intuition on how to fix the definition of a word having the most significant natural color. The problem is that injections are possible at arbitrary points in the word. If the suffix invariant words can only be injected between the consecutive A's in the word, then there is no problem. But how do we define where suffix language invariant words can be injected? Well, perhaps we can get around this problem by using a quantifier. And this leads us to a fixed definition of when a word has the most significant color as its natural color. We now define that a word W has the most significant color as its natural color if there exists an infinite sequence of positions in the word such that no injection of suffix language invariant finite words at these positions changes whether the word W is in the language. Now the words with color 0 in the example automaton on the previous slide all have the most significant natural color, as the sequence can be defined such that the points in the word at which suffix language invariant words are inserted are all between consecutive A's. Now, it is not clear at this point that this is really the definition that we need. Perhaps the updated definition still has other problems, and the fix just made them be hidden in a better way. However, the correctness of the construction for the chain of co-Büchi languages in the paper for this video shows that this is actually the definition that we need. Now that we have a definition for which words should have the most significant color as the natural color, the question arises how we can generalize the underlying idea to the other colors. We have to, in a way, characterize what constitutes the second highest color in a parity automaton. In order to do this, we can use the following idea. In a parity automaton, the second most significant color is the one in which adding flower loops does not change whether a word is accepted or not, except if after the change the most significant color is taken infinitely often along a run. By an orthogonal composition of this idea with the previous definition, we obtain for the second most significant color the following definition. We say that a word W has the second most significant color as natural color if there exists an infinite sequence of positions in the word, such that for all injections of suffix language invariant finite words at these positions in the sequence, so that we obtain a word W prime, we have that either W prime is in the language if and only if W is, or W prime has the most significant natural color, and W does not. The suffix and W does not is there because otherwise the words with the most significant color as natural color would also have the second most significant color as natural color, which makes very little sense. To keep this definition a bit nicer, we will henceforth define not the natural color of a word directly, but in which color a word is at home. This is now exactly the same definition as before, except that the suffix and W does not in the second case is missing. And as the last step, we can now generalize these definitions to all colors. What is now here on the slide is the definition used in the paper for this video. And to simplify the presentation henceforth, we will assume, without loss of generality, that the most significant color is the one with number 0. For every even or odd I, we say that a word W is at home in color I for some language L if there exists an infinite subset of indices J such that for every possible sequence of finite words U0, U1, and so on, if a word W prime is the result of a suffix language invariant injection of U0, U1, and so on at the positions in J, then we have that either W prime is already at home in a color strictly smaller than I, or both W and W prime are in L and I is even, or both W and W prime are not in L and I is odd. While this is now a very complicated looking definition, it captures exactly the intuitions that we have obtained in the last few minutes. And finally, we defined the minimal natural number that a word is at home in the natural color of this word for a given language. Note that for the color 0, the first case here cannot apply. And hence, for the most significant color, performing suffix language invariant injections must not change whether a word is in the language or not. While it is, again, not trivially clear that this idea captures all necessary aspects of the natural color of a word, the correctness proofs of the construction to obtain co-Büchi automata for the decomposed language show that this is the case, and hence we now have a definition for the natural color of a word that is based on the language to be represented alone, and not on an automaton representing the language. Now that we have a definition of the natural color of a word, let us now turn towards the question of how to compute a canonical representation of an omega regular language as a chain of co-Büchi automata. It turns out that the process for doing so is actually quite simple when starting from a deterministic parity word automaton with transition-based acceptance. We first have to make the automaton structured and then streamline it. The two operations, which will be shown next, simplify and recolor a deterministic parity automaton without changing its language. Afterwards, we can read off the co-Büchi automata for the canonical representation from the deterministic parity automaton. These co-Büchi automata are then made canonical using the procedure by Abu Radi and Kupferman. We will use the automaton given above as running example and will consider the first step before having a closer look at the example automaton. A structured automaton has the property that every pair of states with the same language is in the same strongly connected component. For the streamlining construction in the second step to work, we need the parity automaton that we start with to be structured. Making an automaton structured is actually quite easy. We can define an order over the strongly connected components in the automaton and every transition to a state that has a language equivalent state in a later strongly connected component in the order is then rerouted to such a state. Finally, the initial state is adjusted, so that it is also as deep as possible in this order. And then states that become unreachable are removed. Since transitions and the choice of initial state are changed only to language equivalent states, and rerouted transitions are taken only finitely often along every run in the automaton, the language of the automaton does not change when making an automaton structured. However, the automaton may become smaller. In our example automaton, we have two strongly connected components, where the first one consists of the leftmost state and the other strongly connected component consists of all other states. When making the automaton structured, the initial state is changed to Q1, and Q0 can then be removed because it became unreachable. Our example automaton is now a bit smaller, and before looking at the next step of the construction, namely how to make an automaton streamlined, let us have a look at this example in more detail. So, what language does our example automaton represent? First of all, note that the automaton consists of two parts, namely the upper and lower parts. Whenever a D is seen in the word, a run switches between the two parts. The transition from the lower to the upper part has a color of 0. So a word is accepted if switches between the parts happen infinitely often. The states Q1 and Q2 have the same language because for every letter, the transitions within the upper part lead to the same state. Well, that is the case, except for the A transitions. But if at some point only these are taken anymore, the word is rejected, regardless of whether the run was in state Q1 or Q2 when that started to happen. So words accepted from Q1 are also accepted from Q2 and vice versa. However, state Q3 has a different language. That is because a suffix word consisting only of Cs is accepted in the upper part, whereas that word is rejected in the lower part. In the upper part, the color of the word becomes 2, in the lower part it is 3. Furthermore, in the upper part, there are two different colors with which a word, consisting only of A's, can be accepted. Because Q1 and Q2 have the same language, the initial state could also be Q2, and then the color of the word consisting only of A's will be different. So let us keep an eye open for how the natural color is assigned for this word by the overall construction. Let us now come to the second step of the construction, namely streamlining the automaton. The idea here is to change the colors of the transitions to values that are as low as possible. We show how this is done. The construction works by iterating through the colors, for which we use the symbol I henceforth. In every iteration, the algorithm checks if the color of a transition can be lowered to I, starting from I equals 0. For every value I, the streamlining construction first decomposes the part of the automaton not yet recolored into strongly connected components, and it colors each transition between these strongly connected components with the color value I. Here, because we start with a single strongly connected component, there's nothing to do. Then, the algorithm checks in each strongly connected component if the lowest color occurring has the same parity as I. Whenever that is the case, this means that a run taking the lowest color infinitely often has this color as the dominating one, and hence lowering the number to the same as I can be done without changing the automaton's language, because we only do that if this least color has the same parity as I. Here the transition from Q3 to Q1 is changed to color 0, which it already has. So no change here. The streamlining construction now does the following. Whenever a transition has been recolored, it is removed from further consideration, and it is never recolored again. The algorithm now only switches to the next color if no change was previously done to the automaton. In this case, because a transition was just recolored, the construction considers I equals 0 again. Again, the automaton is decomposed into strongly connected components, and the colors of the transitions between those are changed to 0. Here, the transitions between the upper and lower parts now obtain a color of 0 as well. They are then removed from consideration. Again, it is checked in each part if the lowest color has the same parity as I. This is not the case anymore, so the algorithm continues. This time, SCC decomposition does not make a difference and no color is changed. Now finally, the algorithm changes to color I equals 1 and performs SCC decomposition again, where SCC is short for strongly connected component. In both SCCs, the lowest color occurring has the same parity as I, and hence the transitions with the lowest colors in the respective SCCs are changed to 1. The transitions are removed from further consideration, and implicitly also the states that do not have incoming or outgoing transitions anymore. The algorithm continues with checking if there are more changes to colors possible for I equals 1, finds out that this is not the case, and switches to the next color of 2. Again, SCC decomposition does not make a difference, and the lowest color in the only remaining SCC has the same parity as I. The transition colors are changed to 2. After checking if for color 2 there are more changes, the algorithm changes to I equals 3. And this time, it recolors the only remaining transition to 3 and removes it. Now everything is recolored and the algorithm aborts. This is now our final automaton, in which some colors have been lifted. The language of the automaton has not been changed, but some transitions obtained a lower color. With a streamlined automaton, we can now do the last step of our construction. We extract the co-Büchi automata from the parity automaton. The procedure for doing so is actually quite simple. For every automaton for our language Li, we use the same transition structure that the parity automaton has, and define those transitions to be rejecting that have a color of smaller than I. However, whenever there's a rejecting transition to some state in the resulting co-Büchi automaton, we add some more transitions. These have the same predecessor state and have the same label, but they lead to different states in the co-Büchi automaton, for which the corresponding parity automaton state has the same language. Here in this example, this means that whenever there's a rejecting transition to Q1, then there also needs to be a rejecting transition to Q2 for the same predecessor state and the same letter. This is why in each automaton, there are now 2 outgoing rejecting transitions for the letter D from Q3. And that's basically it. We show in the paper that when extracting the co-Büchi automata in this way, from a streamlined and structured automaton, we obtain co-Büchi automata characterizing in which colors a word is not at home. As the final step, the automata can now be made canonical, using the construction by Abu Radi and Kupferman. Here, the automata for L1 and L3 reduce in size, whereas the automaton for L2 does not. This allows us to see more easily which words have a natural color of 0. These are exactly those for which the letter D occurs infinitely often, and hence the words on which Ds occur finitely often have a natural color of at least 1. We can now also see which natural color the word consisting only of A's has. It is color 3 because L3 accepts the word, but L4, which is not shown here, does not, because L4 is the empty language. Let us now conclude. The paper to which this video belongs makes two contributions. The main conceptual contribution is an automaton-agnostic definition of the natural color of a word in a given omega regular language. The main algorithmic contribution is a polynomial time procedure to compute a chain of co-Büchi automata representing an omega regular language in a canonical way. This procedure takes a transition-based deterministic parity automaton, and while we didn't discuss the fact that it runs in polynomial time in the size of the input, all of the steps that we did were quite simple. The procedure for making good for games co-Büchi automata canonical also runs in polynomial time, as shown by Abu Radi and Kupferman. In addition to the content in this video, the paper also discusses how to read off the natural color of a word directly from a streamlined parity automaton. Another thing not discussed in this video and also not in the paper is how these automata can now be used in practice. The interest in canonical automata comes from their practical use, but in this work we have not shown yet that they are of use in practice. So this is obviously future work to be done. If you are interested in doing that, please feel free to contact the authors of this video and the paper, and thanks for watching this video.